Hello and welcome to the 7th lecture of the machining science course. Now, let me remind you that in our last session what we have discussed is the selection of tool angles. Now, as you have understood from the discussion that selection of tool angles, particularly the rake angles, flank angle, cutting edge, tool cutting edge angles, these are extremely important because the cutting forces, surface finish, power consumption of the machining, these are all dependent on the particularly the proper selection of the rake angles. Now, we said that although the cutting force and power consumption reduce if we increase the rake angle, but we have seen that rake angle cannot be infinitely increased because in that case the cutting angle is decreasing and therefore, the tool becomes weaker and less material available for the heat conduction. So, during the machining, because of the plastic deformation and because of the chip sliding over the rake face of the tool, lot of heat is produced and part of it goes to the tool, and if the temperature which is occurring during the machining, if it is not taken out, if it is not conducted from the tool, in that case there will be thermal deformation of the tool. So, therefore, we said that we cannot infinitely increase the value of the rake angle and there is an optimum value at which the tool will be neither very weak nor it will be it will consume lot of power and lot of force. So, we said that there is a range of rake angles, particularly the side rake angle, orthogonal rake angle and the normal rake angle, and the range given was about 5 to 15 degree. Although we said that negative rake angle tools are also used, for example, for the carbide tools when we have to have the strong tool, because there are quite a lot of forces involved in the high speed cutting, and particularly the carbide tools are brittle. So, it cannot withstand the jerks or the sudden increase in the load and so on. So, therefore, the tool has to be strong. So, to make the tool stronger, we have to have the more material and therefore, the cutting angle has to be large and therefore, the rake angle has to be less. So, as less as negative rake angle can be selected. So, these are the discussions that we had last time, and it is very important to select judiciously that how you have you can get the tool properly selected, so that the power consumption and the surface finish particularly become desirable as per the requirement. Well, today we will be discussing the cutting forces in the machining and the merchant circle diagram. This is the mechanistic model which explains the mechanics of metal cutting. Well, let us see. If you look here in this slide, we have the turning operation, and here is the cylindrical workpiece which is mounted with and clamped with the help of the 3-jaw chuck. You understand that the 3-jaw chuck is used for centering, the automatic centering of the workpiece. Although there are 4-jaw chucks and the collet chucks which are also used, but here it is shown that there is a 3-jaw chuck which is used for mounting or clamping the workpiece. Now, during the machining, the forces which are acting, particularly we have the 3 major forces. One is the cutting force, which is the major force, and there is a thrust force which is the combination of the radial force and the feed force. So, let us say here this is the direction which is the direction of the feed force, that is along the direction of the feed, and perpendicular to that is the radial force. Radial force is coming along this. So, it will try to distract the tool from the workpiece, and the cutting force which is vertically located. So, if you see, for example, if it is the tool tip, okay. So, this will be the direction of the feed force, as I said. So, this is the direction of the feed. Now, this is the tool tip, okay. this is the tool tip, let us say. Now, if this is the feed direction, so then in the radial direction we have the force like this. Okay. So, this is the F r, and the resultant force in the horizontal plane, this is called the thrust force. Okay. So, the thrust force becomes equal to F r square plus F f square. F r once again is the radial force and F f is the feed force. So, now if you draw a parallelepiped, for example like this, okay. This. So, in this case, this is the force which is the cutting force F c, all right, and the resultant force will be something like this. This is the R. So, R is becoming equal to root over F c square plus F t square. Okay. F t is the thrust force in the horizontal plane. Okay, and thrust force is given by this root over F r square plus F square. F r is the radial force. So, F r is the radial force and F f is the feed force. Okay. So, what we have is the radial force at the tool tip, we have the radial force, feed force, and their summation is the result of that is the F t, which is the thrust force, which is in the horizontal plane, as you can see. In the vertical plane, we have the cutting force, which is the F c, and this is the cutting force, this is the force which actually is responsible for the power consumption, because earlier we have seen in our earlier lectures that power, let us say this is the product of F c and the cutting velocity V c, and the cutting velocity we said as the pi d n, all right. D is the diameter of the workpiece, n is the revolution per minute. So, this is the V c which is given in meter per minute unit, all right, where this will be in meter, okay, and this is RPM, that is revolution per minute. So, it will be meter per minute. Now, this force, as I said, is responsible for the power consumption, okay, and therefore, this is important that the F c taken or F c consumed during the process should be as minimum as possible, so that the power consumption remains minimum, all right. And what does it mean power consumption is minimum? That is, suppose you are using a machine tool for removing the workpiece material from the job to give the final shape, size, finish, accuracy. So, if the power consumption is very high, in that case the machine will be very bulky, and expensive. So, therefore, the cost per piece which you are making in that machine will be very high. You cannot afford to compete in the market. So, therefore, those discussions that we have in our last class, that we should judiciously select the angles. Okay, these are the cutting parameters like rake angle, for example, of the tool. So, that is only for that purpose that the machining operation can be performed in an optimum way, so that the shape, size, finish, accuracy obtained with a minimum cost. And the cost criteria we will be discussing later, okay, and there we will again come back that how to select the machining parameters optimally. Okay, so, finally, what we have is that we have basic in the turning, for example, we have the F t and the F c, that is the thrust force and the cutting force, and the resultant force is the root over F c square plus F c square plus F t square. Okay. Let us see that how these forces can be correlated together, all right. So, here we have the diagram where we have the workpiece here, all right, chip here flowing along the rake face of the tool, and the tool is taken with a rake angle of alpha. Now, this is the shear plane, and shear plane is the plane along which the maximum deformation, plastic deformation occurs. This is the angle which is the angle between the shear plane and the velocity vector. This is the VC. Okay. So, if you see this, for example, if I draw this line of the parallel to the VC, okay. So, this is the angle which will be phi, which is shown here actually. Okay. Now, if we assume that the chip flowing over the rake face of the tool is a lump body, homogeneous body, and flowing at a constant velocity over the rake face of the tool, then the resultant of the forces acting on the chip from the tool side through the rake face of the tool and the resultant force acting on the chip from the workpiece, which is the reaction force, acting through the shear plane, they will be equal to 0. The summing of them will be equal to 0. What I mean to say is that, in other words, resultant of the forces acting on the chip from the tool side and the resultant of the force acting on the chip from the workpiece side, they have to be equal, opposite and collinear. Then only the chip as a lump body can be moving at a constant velocity over the rake face of the tool. I hope this is clear. Once again I will repeat that here we have a resultant force which is acting on the chip, and this is the resultant force acting on the chip from the workpiece side. Now, this resultant force is acting on the chip through the shear plane, and this resultant force R acting on the chip from the tool through the rake face of the tool. Okay. So, they have to be equal, opposite and collinear, so that their summation will be equal to 0, so that the chip moves at a constant velocity. So, let us say this is the VCH, chip velocity, and this is constant, moving at a constant velocity over the rake face of the tool. Now, this resultant force R can be resolved into two components. One component is F, which is along the rake face of the tool, this is the F, and another which is perpendicular to the rake face of the tool, let us say N. Okay. So, this resultant force we have resolved, or we can resolve into two components, which is F along the rake face of the tool and perpendicular to the rake face of the tool. So, therefore, this F, which is parallel to the rake face of the tool or acting along the rake face of the tool, this can be considered to be the frictional force, and this friction force is appearing because of the normal force acting on the chip from the tool side. So, F is the friction force, N because of the normal force acting N. Now, between the normal force and the resultant force, as we know, the angle made is called the friction angle. So, here the beta is the friction angle between the resultant force R and the N, which is the normal force acting on the chip. Similarly, the resultant force R prime acting on the chip from the workpiece side through the shear plane, this also can be resolved into two components. One which is parallel to the shear plane Fs, and another which is perpendicular to the shear plane, which is Fn. So, since Fs is parallel to the shear plane, so therefore, Fs is considered to be the shear force, okay, and normal to that is the Fn. Okay. Now, if we see that we have four components: F friction force, N normal force, Fs is a shear force, and Fn normal to the shear force. Now, during the machining, when the phi is altered, okay, and the alpha, therefore, the alpha is altered, in that case the direction of the Fs, Fn, F and N, they will be changed. What I mean to say is that during the machining the power consumption can fluctuate. Okay. So, therefore, the phi, which is the shear plane angle particularly, that shear plane angle can change a bit, and if the shear plane angle changes, in that case, as you understand, that Fs, direction of the Fs, Fn, F and N will be changed. So, therefore, we do not have any particular or identical or ideal direction of the Fn, constant direction of the Fn, Fs and Fn. Now, therefore, the r prime can also be resolved into two more components. For example, it is shown here. This is the same r prime we are resolving into two more components, Fc, which is parallel to the Vc, okay, this is the cutting velocity, and Ft, which is perpendicular to the cutting velocity. So, we can do it here in fact. So, suppose this is the Fc and this is the Ft. Okay. This is the thrust force and this is the cutting force. So, Fc, since it is parallel to the cutting velocity vector, so therefore, Fc is called the cutting force, because this is responsible for the power consumption, as I said that Fc the product of Fc and the Vc is the power. So, therefore, Fc, which is parallel to Vc, is the cutting force, and perpendicular to Fc, this is the thrust force. So, then we have the 6 forces components: friction force, normal force, shear force, normal to shear force, cutting force and thrust force. Whatever however F phi changes, that is the shear plane angle changes, now Fc and Ft remain constant, they will not change. They have an identical or a particular constant direction whatever happens with the shear plane angle. That is why the r prime is also resolved into Fc and Ft. So, we have the 6 components and they can be correlated, which was done by Marchants in about 1944, Marchants and Ernst, and that is considered to be the first model which explains the mechanics of metal cutting. And mechanics of metal cutting explaining helped us greatly, because we tried to understand the machining process and we have gone deeper into the machining process with the help of the Marchant's diagram, which is of course a very basic, but nevertheless this is the first treatment given to the mechanics of machining, and therefore, it is important for the analysis of the machining process. So, before they correlated these 6 forces with the angles, okay, there are certain assumptions which have been taken by them, and these are the 8 assumptions which are written here, which are which you can see here. First assumption is the tool tip is sharp. So, tool cannot have any nose radius, and that the chip makes contact with only with the rake face of the tool, because the tool is sharp. Second assumption is the cutting edge is perpendicular to the cutting velocity, and if you remember, this is the one condition which is the condition for the orthogonal cutting. So, therefore, they are assuming that this is a 2-dimensional cutting or the orthogonal cutting. All right. The third assumption they made is the deformation is 2-dimensional. Okay. What I said just now, that is no side spread. What does it mean side spread? Is that I explained during the discussion of the orthogonal and the oblique cutting, that in the orthogonal cutting, since the cutting edge makes a perfect 90-degree angle with the cutting velocity vector, so the chip flows exactly perpendicular to the cutting edge of the tool, and there is no side spread. It does not go, or it does not become inclined to that normal to the cutting edge. So, that is what it is said, that there is no side spread of the chip while flowing along the rake face of the tool. Fourth assumption is the deformation takes place in a very thin zone. Let me explain it to you that this assumption had to be taken because the plastic deformation actually does not happen in a along a plane, it happens along an area. Okay. So, this is actually not the shear plane, but plane is much thicker. So, they have assumed that this deformation is taking taking place in a very thin zone. We will discuss it at a later stage, that when the cutting speed increases, as the cutting speed increases, the deformation zone becomes thinner and thinner, and it can be assumed at a very high speed that this is a plane. So, the deformation, plastic deformation occurring in a plane. So, here they are assuming that this is the plane and not the zone. Fifth assumption is the continuous chip without the built up edge formation. If it is not continuous chip, in that case of course, this assumption, this mechanism or this model will not be valid. Sixth assumption is the workpiece material is rigid and perfectly plastic. Okay. Here I have said that if it can be assumed to be a perfectly plastic and rigid body and moving at a constant velocity, then only the r and r prime will be opposite, collinear and equal. Seventh assumption is the coefficient of friction is constant, coefficient of friction along the chip tool contact length, okay, along this length. So, the mu, which is the coefficient of friction, has to be constant. And finally, they have assumed that the resultant force on the chip r prime applied at the shear plane, this one, is equal, opposite and collinear to the resultant force r, which is here, applied to the chip at the chip tool interface. So, r and r prime, as I said earlier, they have to be collinear, equal and opposite. So, with these 8 assumptions, they have correlated these forces along with the angles. Now, if we draw a circle with a diameter of r or r prime, then all the tips of these components Fn, Fc and Ft, they have to lie at the periphery of that circle, as you understand, because all these forces, all these components are the components of one and the same resultant force, r or r prime, and r and r prime, they are equal. So, therefore, if you make a circle with a r or r prime diameter, then on the periphery all the tips of these components will be lying. That is what actually they are showing in here. So, this is the circle, and the circle diameter is r or r prime. Okay. Then this will be the cutting force, this is parallel to the cutting velocity vector, as we said, and perpendicular to that is the thrust force Ft. Now, Fs is the force which is the shear force, and this is parallel to the shear plane. Perpendicular to Fs is the Fn, okay. And there are two more forces, one is the F, which is parallel to the rake face of the tool, and perpendicular to the rake face of the tool is N, which is normal force. So, as you can see, the tips of all these components, they are lying at the periphery of this circle with a diameter of r and r prime. So, this circle, as you know, as you must have studied in other courses, that this circle is called the Merchant's circle diagram, and this circle explains the mechanics of machining in this following way. Now, between the Fs and the Fc, the angle is the phi, which is called the shear plane angle. Okay. Let us see in this slide, for example, between the Fs, okay, which is the shear plane parallel to shear plane, and Fc, which is here, which is parallel to the Vc. So, here will be the Fc and here will be the Fs. So, between them, as you can see, the angle which is called the phi. Now, between the F, okay, this is the friction force which is along the rake face of the tool, and between this force which is nothing but the Ft, because Ft is perpendicular to Vc, this angle is the rake angle of the tool. So, here if you see that alpha, this is the rake angle, this is between the F and this is parallel to Ft. So, you can assume that this is between the Ft and the F, as I have shown you in the earlier diagram. Okay. Now, we have seen that between the N and the resultant force, the angle is called the friction angle. So, beta is the friction angle, and if we draw perpendicular to Ft, all right, and perpendicular to this which is N, this angle is also alpha, which is the rake angle. Therefore, if this is phi and this is alpha, okay, this angle will be the beta minus alpha, because this is actually the 90-degree angle, okay, this is 90-degree. Now, therefore, this angle will be 180 minus 90. So, this is 90 minus beta, right, and therefore, here you can see that this will be the, this is 90-degree again, this is 90-degree, all right, and therefore, you can see that this angle will be beta minus alpha. Okay. Beta is the friction force, alpha is the rake angle of the tool. Now, if we have this geometry, then from here what we can find out is from the triangles, for example, from here Fs, okay, Fs will be with respect to the r prime or r. This will be the r and the cos of this angle, and cos of this angle is cos of phi plus beta minus alpha. This is what it is shown here, that Fs is equal to r and the cos of this, and Fn which is perpendicular to that, therefore, will be r and the sine, because it is perpendicular to that, and the angle will be the same, phi plus beta minus alpha. So, Fs and Fn we have determined analytically. That means, what I mean to say by analytically is that if r is known, if these three angles are known, then Fs can be found out. Let us say at this moment like this. Fc similarly, Fc will be r and the cos of this. So, that is what it is shown here, Fc is r cos beta minus alpha. Ft which is perpendicular to that will be r sine of beta minus alpha. And finally, we have the two forces, which is friction force F, which will be r and the cos of this, right. So, cos of this will be cos of 90 minus beta, and this will be sine beta. Now, this is the friction force r sine beta. Therefore, the N which is perpendicular to the friction force F, this will be equal to r and the cos beta. So, we have all 6 components we found out from the Merchant circle diagram through the angles, and these are the 3 angles particularly, that is the rake angle, which is once again which defines the inclination of the rake face, and this is the angle between the rake face and line perpendicular to the cutting velocity vector, that is one. Second is the friction angle. Friction angle is between the resultant force and the normal force or the normal component of the resultant force, which is perpendicular to the rake face of the tool. And the third is the shear plane angle, which defines the inclination of the shear plane, and which is the angle between the shear plane and the direction of the cutting velocity vector. So, these 3 angles are important, they relate all the components with the resultant force, all right, and how it can be manipulated, how we can find out finally the analytically the cutting force and other components, that I will discuss in the next lecture. Thank you for your attention.